Greetings to all students. The history of science reveals that many significant discoveries have been made while carrying out experiments. In the growth of physics, experimental work is as important as the theoretical understanding of a phenomenon. I am Aparna Raju, Faculty of Physics, Delhi Public School, Bangalore East, and I will take you through the experimental assignments for grade 12 physics under CBSE curriculum. As the COVID-19 pandemic runs its course, educational institutions have put in place alternative methods for students and teachers to continue with their lessons, even practical sessions when attending school is not possible. Delhi Public School, Bangalore East is recreating the lab experience entirely online. This approach enables key concepts to be explored in a practical way that is streamed to a student's monitor. It also maintains a high degree of interactivity since multiple students can be logged onto the same experiment at once. We will also be using OLab simulators where one gets a virtual experience of conducting the experiment. But there are downsides of this approach too. The hands-on element is removed. So here we go and hope all of you are ready for this unique experience. So we begin with experiment 1 to determine the resistance of a resistor using meter bridge. The apparatus required: meter bridge, battery eliminator, galvanometer, resistance box, jog key, plug key, resistance wire, meter scale, connecting wires. The theory behind the experiment is very important. We use the principle of Wheatstone bridge to find the resistance of the given resistor. Actually, we have a wire. The unknown resistance is in the form of a wire. We need to find that, and it is denoted by X in this circuit diagram. So we follow the Wheatstone bridge, which is then converted to a meter bridge. So in a Wheatstone bridge, you have, in the balance condition, you have R by P is equal to X by Q. When is the balance condition? When the current through the galvanometer is equal to 0. And when does this happen? When potential at D and B is the same. There is no current through the galvanometer, and galvanometer will show 0 deflection. So corresponding to this Wheatstone bridge, we are having the meter bridge. The meter bridge here, the resistors P and Q are denoted here, P and Q, and the wire runs from the meter bridge wire runs from A to C. The length of this wire is 100 centimeters or 1 meter, and this is divided into two resistors by the jockey, which can slide over this wire AC, and divide it into two, P and Q. So we keep varying the resistance P and Q till we find the balance condition, that is current through the galvanometer is equal to 0. And this is R and X. Of course, R is a known resistor. We have 5 trials for this experiment, and we vary the resistance of R from 1 to 5, and we find the value of X, the mean value of X from 5 different trials. So how do we calculate? We know R, we know P, we know Q. How do we calculate P and Q? Because there's only length over here which you will know. So when the galvanometer reads 0, we need to measure this length, and this is denoted by L, and this is 100 minus L denoting Q. So P, we know the formula. P, any resistor, is equal to rho L over A. So P is equal to rho L over A. Rho is the resistivity of the manganese wire. We are using the manganese wire as the meter bridge wire. And Q will be equal to rho 100 minus L. Length of Q is equal to 100 minus L over A. So we know P, we know Q, and then we know R. So the unknown is X. So X will be given by QR by P, which is equal to Q. Substituting for P and Q, you will get rho, X is equal to all the other terms. A and rho will get cancelled, and you are left with 100 minus L into R by L, where L is the balance length and R is the known resistance. So this experiment only involves in determining the balance length L for 5 different readings. So we start here with the positive terminal. So this is the positive terminal of the battery, and we will be connecting the positive terminal here from the positive terminal you have it connected to point A of the meter bridge. So this is the positive terminal and we run through it, and this is terminal A. So I am going to connect it here, and from A the connections move like this, which is internally connected over here like this, and we reach the point here where R is connected. So we need to connect R between these 2 points. Okay. So this is R. So how does this work? These are the 2 terminals of R. Whatever resistance I need to include, that I need to unplug it. So for the first trial, we will be using 1 ohm. So this is 1 ohm, and I have unplugged 1 ohm. So 1 ohm right now is the resistance of capital R. Then we move on to X. So this is again internally connected. Okay, I'll come back to D later. This is internally connected, so this is internally connected. This is point D where we need to complete the connections. So here we are going to connect X. Across these 2 points, these are the points, which corresponding points are here, and we have connected the wire across these 2 points. Again, this is internally connected here, and we reach the terminal C here of the meter bridge. So from C it goes to plug key. So this is C. So we will be using the crocodile tip there, and then we have this connection to the plug key, and other end of the plug key goes to the negative of the battery. So the other end of the plug key will move to the battery negative terminal. So this is the other end of the key, which moves to the negative of the battery. Now you can see that the battery has variable voltages, which varies from 0 volts to 12 volts in steps of 2 volts. It's enough if we use a low voltage of 2 volts. So we will be using 2 volts for this experiment. And the last part of the circuit, from D, I need to connect it to B. So this is the terminal D, and from there we take a wire from there, D, and this is connected to one end of the galvanometer. So I could choose anything, plus or minus, it doesn't make a difference in these terminals. So I choose minus, and here, because galvanometer is center 0, so it is just the direction of the current. If it is reversed, then it will take the other side of the scale. So the positive and negative do not matter, and the other end of the galvanometer, now is connected to a jockey. This is the jockey. It is connected to the jockey, which is able to slide on meter bridge wire. Now we will be checking if our circuit is correct. So we put on the battery and ensure that this is at 2 volts. So this is at 2 volts, the battery is at 2 volts. And how do we check if our connections are right? If we place the jockey at one end of the meter bridge wire, say if the galvanometer deflects to the right, then when I place it at the other end of the meter bridge wire, it should deflect to the left. So the deflection on the extreme ends, when the jockey is placed at the extreme ends of the meter bridge, should be opposite. Then only I will get the null point somewhere in between and my circuit is working and correct. So let us test if the circuit is correct. So I take the jockey, I place the jockey on the left of the meter bridge, and you can see that the deflection in the galvanometer is to the right. Now when I place the jockey to the right, the deflection is on the other end of the galvanometer. We will start with the first trial where R is equal to 4 ohm. We will remove 4 ohms from this box to include that resistance. So this is 2 and 2. We have removed 4 ohms and tighten the other keys so that the resistance is not included in the circuit. Now we put on the battery and we need to take the balance length L. So we check for the circuit, so it's deflecting to the right and it is deflecting to the left. So we will find the balance length where exactly we are going to get the balance length as we slide down on the meter bridge. Yes, somewhere here. Yes. Now you can see that the galvanometer reads 0. The galvanometer reads 0. And we need to measure the balance length from the left side. So we are going to use the scale, the top one, the top scale, and when we read the scale, we are getting, you need to take the readings, it will be focused on that and you need to take the readings. Please post your readings in the chat box. You need to take the readings. You need to take the readings on the meter bridge. Take the corresponding balance length on the meter bridge and post your reading, that is the balance length L, and post your readings in the chat box. Okay, have you completed taking the readings? The remaining part are just calculations. You will have to find X. We will move on to trial 2. We will unplug 5 ohms from the resistor R. So for the last trial we had unplugged 4. So now one more. So 2, 4, 5. We will tighten all the other keys. We will put on the battery. We will check the circuit for opposite deflection. So I am keeping the jockey on the left, the deflection is to the right, and to the right the deflection is on to the left, and then we find the balance length. Yes, the galvanometer reads 0 and the balance length. You need to record the balance length. Record the balance length and keep posting in the chat box. We move on to the third trial. We'll unplug 6 ohm from the resistance box. So we have already unplugged 5, and so maybe I'll remove this 5, put it here and here. So this is 5 plus 1, 6. 5 and here is 1, 6. Tighten the other keys. Okay, so next step is put on the battery and check for opposite deflection. It is deflecting to the right and here to the left, and then I need to take the balance length. Slowly, so right. Yes, I have got the 0 deflection in the galvanometer, and you need to record the readings, the balance length. Please record the length and post your readings in the chat box. So we move on to the fourth trial. 7 ohm we have to unplug from R. So this is your R, this is 5, and I'll remove 2 ohm from there and tighten all the keys. So you have 5 plus 2, 7 ohm. We put on the battery and check for opposite deflection. So it is deflecting to the right and then the other side to the left, and then we will find the balance length. Yes, it is almost 0. Yes, the galvanometer shows 0 deflection. There is no deflection in the galvanometer, and we need to record the readings on the scale. So from the top scale, from the left hand side, we have to take the readings. So we use the top scale, and please note down the readings. Note down the readings. Okay. So we move on to the last trial. 8 ohms we need to unplug from the resistance box. So this is 5, 6, 7 plus 1, 8. So 8 ohm, we'll tighten the other keys and we'll check, we'll put on the battery and check for opposite deflection. So it is deflecting to the right and here this side to the left. Then we will take the balance length. Yes, the galvanometer reads 0 here. So you can see that the galvanometer has no deflection. There is no current flowing through the galvanometer, and then you need to record the balance length for the same. So you can see the balance length, the top scale you need to use. Check your reading on the top scale. Please take your readings from the top scale. Now you need to fill up the tabular column. Hope you have taken readings and filled up this column. And next you will have to find X. 100 minus L into R over L. You need to calculate these columns. You can go ahead, take 2 minutes and finish with the calculations. And then we will find the result. you could verify your observation tabular column, the R values, the L values, the X which you have got from this tabular column. So the first trial X is 1.7 ohm, the next one 1.8, 1.7, then 1.8 and 1.8, for which the corresponding balance length that you had to record was 70, 74, 77.5, 80 and 82. Note down the result, the last part of the experiment, but the very important part, you need to note the result. The value of the unknown resistance X was found to be 1.8 ohm. We will run through the sources of errors. Contact potentials are small voltages that may occur at the junction of two dissimilar metals, for example between hookup wires and winding posts. The thermoelectric EMFs occur between dissimilar metals when there is a temperature difference between the two metals. Their effect on the measurement may be an error of either positive or negative sign depending on the sign of the temperature difference. Resistance of connecting wires, internal resistance of the power source, resistive heating of one or more arms of the bridge, changing their resistance, insufficient sensitivity of the galvanometer and non-uniformity of the slide wire. You would have to keep in mind the following precautions. Do not press slide wire down so hard as to dent the wire, and do not slide it while pressing it down, for that can scrape the wire. The uniformity of the slide wire resistance depends on it being uniform in physical cross section. Physical damage from denting or scraping can destroy this uniformity. Switch the known resistor and the unknown resistor around so that R was in X's place and vice versa. This helps to compensate errors arising from the non-uniformity of the so-called uniform wire. Use a voltage of 2 volts to prevent burnouts. Galvanometers are sensitive instruments. High currents can damage them. A low current prevents overheating as well. Now this is an assignment for you. You need to find the answers to these questions. The resistance of connecting wires could cause error. Only some of the wires are critical. Which wires need to be short and which don't matter? Explain. What effect does the battery voltage have on the precision of the bridge? What effect does the galvanometer sensitivity have on the precision of the bridge? Would one twice as sensitive give twice the precision? What if the voltage of the power source you were using varied erratically, say by as much as 20%? What effect would this have on your experimental data and results, and how much? Considering only the errors due to the uncertainties in resistance of the bridge arms, show that the slide wire bridge is most precise when the slider is set at the center of the slide wire. By changing the value of the resistance box R, the slide wire bridge may be made to balance at any desired point along the length of the slide wire. If it were balanced at a point 2 centimeters from one end, how would the accuracy of the measurement compare with a measurement of the same unknown resistor made with the balance point at the center of the wire? Students, hope this session was fruitful. Remember to note the date, enter your observations in the record book and practice on simulators. With this, I take leave. Next time, next experiment. Thank you.